Modern cloud security relies almost entirely on logical software abstractions. We configure operating systems and hypervisor permissions under the assumption that the infrastructure will faithfully execute those rules. But in a virtualized environment, software can be manipulated to lie. Sophisticated adversaries exploit this through ring-1 attacks. Instead of picking the lock on the operating system, they punch right through it, compromising the foundational hypervisor layer that controls the hardware directly. If the hypervisor layer underneath your network is actively hostile, traditional security tools fail. Endpoint detection, firewalls, and audit logs only report what the hypervisor allows them to see, leaving the guest OS functionally blind to introspection. When standard software policies inevitably report false information, survival requires anchoring trust to something that cannot be spoofed, the immutable laws of physics. In this environment, true data sovereignty cannot be granted by an administrative checklist. It must be derived from physical evidence that exists independently of the software stack. We've already seen the cost of logical failure. During the Microsoft master key breach, a standard software crash inadvertently leaked a sensitive master key into a persistent disk state during the snapshot gap, the brief temporal window before the system fully shut down. To counter these persistent threats, Vapor Audit deploys a hermetic panic protocol. It adopts a fail-dead posture, prioritizing the immediate destruction of sensitive data over system availability. This diagram illustrates a specific vulnerability in how code is built. Modern compilers frequently identify key wiping routines as redundant and silently remove them to optimize speed. This leaves the sensitive data intact in a memory block, even after the program thinks it's been cleared. Vapor Audit bypasses this optimization by using ptr.write-volatile. This explicit command forces the CPU to physically overwrite the RAM with high-entropy noise, ensuring the data is scorched regardless of compiler logic. Immediately following the overwrite, the system executes a process.abort command. This kills the process instantly without unwinding the software stack, blocking attackers from hooking into cleanup routines to capture the system state. By shrinking the window of exposure to a few dozen microseconds, the protocol ensures that even a successful memory snapshot captures nothing but noise. Logical geography is just as fragile. During the Snowflake data lake heists, attackers bypass geographic restrictions by routing stolen credentials through VPNs, making their unauthorized access look like a legitimate local connection. Vapor Audit replaces spoofable IP metadata with latency triangulation. It verifies physical location by bouncing raw TCP sockets off highly secure physical anchors, like this facility at Cheyenne Mountain, known as Alibi nodes. This verification relies on a foundational physical constant, the speed of light in fiber optic glass, which propagates at approximately 200,000 kilometers per second. This map shows how measuring the round-trip time of a packet to these nodes establishes a maximum geographic radius. When these circles intersect, they define a feasible region that cannot be spoofed by a virtualized coordinate. If the physical latency exceeds a strict 15 millisecond threshold, the system mathematically proves the hardware is in the wrong location and kills the connection immediately. This turns geographic sovereignty into a physical measurement, making software-based location spoofing a violation of causality itself. Even when credentials are valid, lateral scraping attacks, like the 23andMe breach, show that data can be observed maliciously without triggering a single logical alarm. To detect this, Vapor Audit uses a microcode Sentry. It is grounded in the principle that all observation requires energy. A hypervisor cannot inspect memory without consuming shared physical resources. This bell curve represents the statistical baseline for normal CPU execution. When an adversary attempts to inspect cache lines or pause the system, they introduce microarchitectural friction, an energy shadow that slows down the code. The Sentry continuously pulls the hardware timestamp counter to measure CPU cycle variance. If that variance drifts past a strict 3 sigma threshold, as shown by this data point landing outside the curve, the system detects the interference. Because this detection happens at the silicon level, a hostile hypervisor cannot peer into the enclave's memory without creating a detectable thermodynamic disturbance. This architecture ensures that master keys are never stored on a disk where they can be forensically recovered or copied. Instead, keys are reconstructed from independent shards in volatile memory, only after the system passes its physical location and thermodynamic integrity checks. The key exists for mere microseconds to execute its task, then it is eradicated. This effectively eliminates the time window an attacker needs to capture the system state. This shifts compliance from a series of mutable logs and administrative claims to a time series of measured physical constants. In a hostile digital landscape, security cannot be a matter of policy adherence. It must be a verified physical state.